Good morning. You are welcome again to the subject manufacturing processes 2. We are continuing module 2 mechanics of machining, and the area we are covering presently is the mechanism of chip formation, which is a part of mechanics of machining. Today is the lecture 7, use of chip breaker in machining. So, it is a new feature, chip breaker. Now, what are the specific instructional objectives of lecture today? To enable the students at the end of this lecture identify the need and purpose of chip breaker, illustrate the various principles of chip breaking, design simple type of chip breakers, demonstrate configuration and working principle of some common chip breakers, state the overall effects of chip breaking. Before I go into this one, let us have a look into the chip breaking, the necessity of chip breaking. Suppose this is a job going to be turned. A rod being turned by a cutting tool like this. This is the cutting motion, the rotation of the job, and this is the feed motion of the tool. Now, the chip that will be produced will come through this side. In this direction the chip will flow. If the work material is brittle, then the chips will be discontinuous type of irregular size and shape, small pieces, they will automatically fall into the container at the bottom. But if the work material is ductile and a cutting tool is having say positive rake or favorable rake, then the chip will flow continuously if it is a ductile material, and this will tend to go flat just like a sword. If we increase the cutting velocity, this chip will come out at very high speed just like and the edges will be very sharp just like sword. It is more than a sword because it comes out at very high speed, and secondly it is very hot immediately after machining. Now, this chip which is coming out at high speed continuously as a hot beam is very dangerous to the operator as well as the people who will be working in other machine tools around. Secondly, this chip, if not broken into pieces, or if this may entangle with the cutting tool, it can entangle with the job and spoil the quality of the job. So, these are the problems which may come up if the chip is allowed to come at very high speed continuously as just like a hot sword. Now, let us come to the summarizing major problems with continuous chip that generally develops in continuous type of machining, ductile materials, danger to the operators that I explained already, damage of the finished surface if it is allowed to entangle with that, difficulties in chip disposal, the collection of the chip and disposal of the chip becomes also extremely difficult if the chips come out in that continuous form. Now, the need and purpose of chip breaking. Now, to control this problem, to overcome such problems, some action has to be taken, and this is done by what is called chip breaking. All right. By chip breaking. Now, what is the need? Safety of the working people, protection of the finished surface, easy collection and disposal of chip. These are essential, that is called need. And purpose, improvement in machinability. So, if we apply proper chip breaker, which will not only break the chips in a suitable form and provide safety, protection, etc., this will also help us give good machining or improved machinability. Now, ideal chips of ductile material. So, the problem of chip comes from machining of ductile material, which produces continuous chip. In case of say brittle materials, this problem does not arise, because the chips are discontinuous and they fall automatically into the collector. Now, the closed coils, the ideal, there are two types of ideal chips. One, say this is the tool and this is machining a job, say turning. Now, the chip that will come maybe in the form of a coil. You can see like this, like this. Okay. Now, this will continue. If it continues, there is nothing problem like danger, but the collection and disposal problem. So, if it is made to break at regular distance in the form of small coils, then it is very ideal. It is neither dangerous nor difficult to collect and dispose. The other type, the convenient or ideal type of chip, is the broken chips of regular size and shape. This is like this. Suppose you machine a rod with a tool. Now, the chips will come out and at regular interval it will break in the form of comma shaped or half turn. These are the various shapes. If the chips are allowed to come or made to come into this half broken or broken into half turn or quarter turn chip in the comma shaped, like this comma shape, then this is very ideal. It is neither dangerous, it automatically falls under gravity at the collector, and it will not damage the tool nor the job. So, these are the two forms of ideal chips that have to be attained. Now, there are basic two principles of chip breaking. The continuous chip of machining ductile materials can break in two methods, either self chip breaking or forced chip breaking. Sometimes the chip breaks self automatically, then no need of any extra effort, but sometimes if it does not automatically breaks, some forced chip breaking has to be adopted. Now, self chip breaking, this can be natural or it can be slightly artificial like. Now, natural chip breaking takes place due to the curling of the chip. You will always find in machining ductile materials, the continuous chip, even it forms continuous, it becomes curved or tends to become curved. Why? Because the velocity at the outer end and inner end are different. At the rubbing surface, the velocity is high, and the inner and this exposed surface, the velocity is low. Beside that, these two surfaces of the chip are subjected to different cooling rate, or the cooling are different, will be effective at the outer surface and the rate will be different. So, this will become further curled and work hardened. Then after some time, when it will be cooled, solid and say elastic type, and there will be spring back action in this direction, spring back action, then this will tend to break in the opposite side bend and this will break. So, this is called natural breaking, and this depends upon the work material, tool geometry, the thickness of the chip and the rake surface and cutting velocity, feed and all these things. So, this will not happen every time. When these condition will be favorable, then only this will break automatically, that is called self breaking. Now, again what happens, the chip curls. If the chip during curling it hits the work surface, say the unmachined work surface, then there will be further bending and the chip will break into pieces, and this again will come and hit it, it will break into pieces, again this will come and hit and it will break. So, this will continue. So, though the material is ductile, the chip will be continuous, continuously broken into chips of same size and shape. There is another way, that the chip which will come out here in the third one, this will come out and hit the flank surface of the tool, because there is a natural curling tendency, and after curling this will hit at the flank of the tool, and then this will break here, because by this time it has become work hardened and brittle. So, this will break, and this will continue, and say broken chips of same size and shape will continue. This is called, these are all self breaking, but sometime this radius of curvature becomes so large that it does not break, either self breaking or like this or like this. It tends to move very fast like that. In that case, some obstruction has to be created to the flow of the chip. So, this is the chip that is bent or curled. Now, by the obstruction, just like a heel here, by this obstruction, this chip will be forced to bend further or curl further, and this has become already elastic after coming out from the hot zone. So, this cantilever beam, which has already been elastic, will break here where the stress is, bending stress is maximum, and this will continue. So, this chip is forced to bend further, curled more tightly under work hardened condition. So, this will break as a cantilever beam. This is called forced chip breaking. So, a heel is provided here to obstruct. Now, this heel of forced chip breaking can be attained in two ways. One may be inbuilt type or clamp type. Inbuilt type means this cutting tool is a single piece and a groove is cut into that. So, this is a part of the hole, and this form of this groove allows breaking. And clamp type, in a clamp type, this upper part is made as a separate piece. The cutting tool is flat, and the upper part, which will function as a obstruction or heel, will be a separate piece that will clamp to the base tool. This is called clamp type. Now, inbuilt chip breakers. Inbuilt chip breakers may be step type. Inbuilt chip breakers may be step type, or it can be groove type. Now, here this is the cutting tool holder, for example, the cutting tool holder, and this is the tool bit here. Okay. Now, here you cut a groove is cut. This piece of the carbide tip or say high speed steel may be brazed or fixed by brazing on this tool shank, and then a groove is cut. Here also a groove is cut like this, different types. So, this is called step type. So, one step is made. So, there will be a flat surface horizontal and vertical surface here, all right. So, this will be like this. So, this is the horizontal step and this is the heel height. So, this is called step. This material is removed by process. Now, step type may be of 4 category. This is called parallel shaped, which is most simple and easy to manufacture and used very commonly, and this is straight, but it is slightly curved radius at the end. This is very suitable for heavy duty cut at high speed, feed depth, etc. And these two are the angular steps, where the step is angular, made either angular in the widen this direction or widen in this direction. This is called positive angle, this is called negative angle. Here the chip will be curled or broken. If it is curled, then it will be shifted from the workpiece to the operator, because workpiece has to be protected from damage, and sometimes the protection is required for the operator, and the chip will be shifted towards the jobber away from the operator. The curling will take place like this, and in this case curling will take place like this. In this case the chip will flow like this, and in this case the chip will flow like this. Now, groove type chip breaker. Here on the rake surface of the tool, a groove is cut, and this is sufficiently deep, all right. And now, this groove, here is another groove. The two types of grooves are there, one is circular groove and one is tilted V type. Here you see that the radius of curvature of the groove should be smaller than the radius of curvature of the chip. at which it is supposed to break. Now, when the chip will come, this will hit here as an obstruction, a force will act on this. So, this will bend in this direction, and because of the cantilever action, lot of stress will develop here, and this will break into piece, and this will continue. In this case also there is a gap. So, this is there, and when the chip will come, in absence of the heel, this will go straight like this, but because of the presence of the heel, this will force the chip in this direction and bend and as a cantilever beam, and it will break here, and this will continue. Now, let us come to the characteristics of inbuilt chip breakers. Just now you have seen inbuilt chip breakers, which I explained. Now, provided these inbuilt chip breakers are group type or step or group type, provided as an additional geometrical feature like step or group after or during manufacturing of the tool. If the cutting tools are made of high speed steel, then normally these grooves or steps are cut after manufacture of the cutting tool. But if these are made of exotic materials like carbides or ceramic, which are very difficult to process, then these grooves or steps are manufactured during the manufacturing process, like say compaction and sintering process. This is has to be done. Next is the heel of the step or groove causes the chip breaking by further bending and straining. So, this is an obstruction which further bends and strains the chip, which breaks into pieces. This inbuilt chip breakers are very simple in configuration with slight modification, easy to manufacture and inexpensive, cost is low. But the geometry of the chip breaker once made becomes fixed, that is the length of the groove, depth of the groove, that remains same. Now, so that will be suitable for a particular radius of curvature of the chip. If the radius of curvature of the chip changes, then this groove which has been formed already may not be effective, and this radius of the critical radius of curvature at which the chip breaks depends upon the work material, the tool material, the cutting velocity, feed. So, this fixed type chip breaker will be suitable for a particular material and a particular condition. Hence, it is said that this group type or inbuilt chip breakers are effective only for limited range of velocity and feed for a given work material. Now, let us come to the forced chip breaking by clamp type chip breakers. Here, this is a clamp. There are three types of clamp type chip breakers. As I told you that in clamp type chip breakers, this is the cutting tool, flat like, maybe a carbide tip, and then a separate piece is fixed here and clamped here. So, when the chip will flow, the chip will be obstructed, the flow of chip will obstructed by the heel of the clamped chip. Now, here you see that this is the cutting tool, and the upper one, this upper one is the chip for chip breaker. So, they form a groove like. So, when the chip will come, it will hit here and break, but this is fixed. Once made, is fixed, there is no flexibility. So, this is suitable for a limited range of cutting process. Now, this is slightly versatile, where the width of the land, this portion can be varied depending upon the cutting velocity. So, this clamp type chip that can be shifted along the rake surface by loosening the screw and the clamp, and this gap, this flat surface on which the chip will flow can be varied, and depending upon the radius of curvature. But here it is slightly flexible, only the width can be varied. But here is another more versatile, where not only the width can be varied by shifting the position of this one, but the angle, this angle can also be varied by raising this upward and tilting around this axis. So, this is more versatile, which covers a wide range of material, cutting velocity, feed, depth of cut, and so on. No, the design principle of simple chip breaker, design principle of chip breaker, but simple or clamp type, what might be, but it should be simple type, maybe step type. Suppose it is a step type chip breaker. This can be a inbuilt type or it can be a clamp type also. This can be a clamp type also, this part. Okay. What it might be? So, these are the two features, important geometrical feature. One is the width of the land W and other one is the height of the heel. So, these two parameters has to be chosen, so that this chip undergoes the requisite amount of bending. So, the radius of curvature decreases and lot of stress develops here and it breaks into pieces. Now, lot of research has already been done in this area. What has been done? That the critical radius of curvature at which a particular chip breaks depends mainly upon the chip thickness of the uncut layer, this thickness. All right. This thickness at what, this is a critical radius of curvature at which the chip will break will depend upon this uncut chip thickness, this one called A1. Now, here the research data have been put here. This indicates this is one and the chip thickness A1 and this is the radius of curvature, critical radius of curvature. So, this is the region where the chip will break effectively, and this is the area where they will be overbroken, overstrained, more energy will be wasted, and this will be underbroken area where the chips will not break properly. So, this has to be done. Now, how the design has to be accomplished? Say we are conducting a machining work, we know the value of A1. What is A1? A1 is equal to the feet multiplied by sine of the cutting edge angle phi. Okay. ASO sine phi. So, these parameters are known. So, for this A1, say for a particular value of A1 like this, this is the region where if the radius is brought to this level, then the chip will break. Now, suppose we choose a particular radius of curvature for that particular A1 given. Now, putting the value of rho here into this equation, because from this geometry you can see this is the radius of curvature of a circle, this is the chord W and this is the height, and this is the expression W square will be 2 rho, the diameter of this one, minus h, the heel, and h. Now, from the given value of A1 and ASO and phi, A1 has to be determined. From A1 the rho will be determined. You put in the rho, and now you assume any particular value of h, say 2 millimeter or say 1 millimeter, and we get the corresponding value of W. And this is how this type of simple step type chip breakers are designed. Now, if it is a clamp type and with an angular clamp, is an angular clamp where the chip is now flowing like this, is a clamp type chip, design of clamp type, simple clamp type chip breaker with an angle. This is the W width and this is the angle of the breaker, and this is the radius of critical radius of curvature at which the chip is supposed to break. And suppose this angle is beta, then what we do from this geometry? From this geometry we get W, this W is equal to, this W is equal to rho tangent of beta by 2, this is beta by 2. And what is h? This small h here, this is equal to W, this is W sine beta, this is, if this is W, this is also W, and this height is equal to W sine beta, and capital H, that the total height will be small h plus 1 to 2 millimeter, the total height of the clip or the clamp. Now, where rho has to be, this rho critical value has to be obtained from, that is a function of the uncut chip thickness, which is ASO sine phi. These two values are known. From these two values A1 is evaluated. From this A1, from the previous chart, this critical radius of curvature will be determined, and that will be put into this equation, and beta will be assumed, maybe say 45 degree, 60 degree like that, or up to 45 to 90 degree. then we get the value of W. This is how the chip breakers of this kind is designed. But this relation of A1 and this rho A1, the uncut chip thickness, and the critical radius of curvature of the chip at which it is expected to break, should be taken from the chart. Now, here is the result of lot of research that has been already done for design of the chip breaker. This chart shows say design data for step type chip breaker. This is a step type chip breaker, all right, and this is the step width W and this is the height H. So, these are the main parameters. Again, at this corner you see there is a radius, a curvature of radius small r. Now, see the table feed, as I told you that the critical radius of curvature for any work material depends upon the cutting velocity, feed, etc., depth of cut also. So, the value of H and W will depend upon at what feed you are carrying out the work, at what depth of cut. Suppose these are the different feed range 0.15 to 0.3 millimeter per revolution, 0.3 to 0.4, 0.4 to 0.6 and so on. And depending upon the feed, the radius r should also vary. It should increase proportionally with the increase in feed, say 0.25 to 0.6 and so on. Height may be of varying, you can assume it, say 0.25 millimeter, 0.4 millimeter, 0.5 millimeter and 0.75. This is the depth of cut. Suppose for a given value of feed, say at this feed range we are working, and this is the corresponding radius of curvature, and this is the height already assumed, say for light speed, all right, light speed. And then what will be the value of W then? If the depth of cut is 0.4 to 1.2 millimeter, that is low duty cut, then W should be 1.6. If the depth of cut is increased, then this should be slightly increased gradually. And as the feed is increasing, you see the value of H, the height, is also increasing and W is also increasing, because with increase in feed or the feed A1, the radius of curvature at which it will break will increase, for which value of H and W should increase. As so increase in feed, you see that the H is increasing, at with H is W is also increasing. So, these two. So, this is a table which can be utilized very simply by the people to prepare either the step type or say inbuilt type or say clamp type chip breaker. Now, integrated tool geometry with inbuilt chip breaker. Now, inbuilt chip breaker, as I told you, can be step type or group type, and those are created on the rack surface of the tool by say during manufacturing or after manufacturing, by grinding or by powder metallurgical process during compaction and so on. So, this is basically, in this case, suppose here this is the rack surface of the tool, we make a groove. This groove, a tilted V groove, that is created for breaking the chip. This is the heel portion, F is the heel portion, that exerts a force and the chip is forced to bend further, and because of the stress it will break. Now, while making this chip break, other factors are also taken into account to derive the benefit of such. That means, factors considered while designing integrated tool geometry. Why it is called integrated tool geometry? The chip breaking, inbuilt chip breaker plus some other features which will provide further benefit. What are those factors? These factors are mechanical strength at the cutting edge. The cutting edge, if left very sharp, then it will become mechanically weak. So, it has to be rounded. Here you see from B to C it is curved, this is called edge rounding, and this is done for strengthening mechanically the cutting edge. Sometimes it is beveled also. Then from C to D, this portion is a flat portion, and that is the negative break, and that is also for mechanical strength. Then the chip breaking, this is the chip breaking part, D, E, F for chip breaking, and favorable rake for reduction of cutting force. Now, here this slope, this is the rake angle, this rake angle should be possibly positive, so that the cutting force, the chip flows easily timing, and then the cutting force will be reduced and power saving will be there. So, this should be positive followed by negative for strength, followed by positive for reduction of cutting forces. Control contact cutting effect, that means this chip tool contact length, that means it causes rubbing, this should be reduced, and if you can reduce it by modifying the tool geometry, that is called control contact cutting effect, that is to be automatically achieved. Further, better heat dissipation, if you make this end instead of very sharp edge some flat and then curved. So, this is a flat type or type, the heat will be very quickly dissipated and the temperature will not be concentrated. So, there will be no stress concentration, no thermal concentration, heat concentration. So, these are the advantages. Now, here you can see some of the standard chips, all right. Inserts, these are carbide inserts, the colors are say coated insert, titanium nitride or titanium carbonitride coated inserts, is a turning insert, is a copying lathe, copy turning, is a triangular, is a rhombus type, and this is also a rhombus type triangular. There are different various shapes for various purposes the bits are made. These are basically tungsten carbide, cobalt mixed sintered carbides. And now, what you have to see commercial inserts with integrated tool geometry. As I told you, the integrated tool geometry. So, on the rake surface the tool geometry is provided not only for chip breaking, but also for mechanical strengthening, then control contact cutting effect, reduction of cutting force, all these factors are taken into account. Now, as a result, these you see the profile of the rake surface becomes quite complex, very complex. Some of them is called pattern like. Now, earlier days it was very difficult, because providing such typical geometry or configuration or a pattern like it was very difficult, particularly when the work tool material was ceramic or carbide brittle material. But nowadays it has become easy, because of the advent of number one is the sintering process, improvement in the sintering process. In a compaction process, the tool by which the compacting is done before sintering, those are given this typical shape by electro discharge machine, electrochemical machine, which was not available earlier, but nowadays these are available, and the design part can be very comfortably and quickly done nowadays with the help of computer, that is computer aided design. So, with the advent of computer aided design and these processes like EDM and ECM and the easy compaction and sintering, such kind of very difficult patterns with to give the integrated chip tool geometry has been possible, and now these are very popular and are widely used. Now, this chip breaking is not only used or confined to say carbide tools or say ceramic tools, those are adopted in high speed steel. Here you can see the on the high speed steel tools. Now, high speed steel is very primitive tool material, which was invented around at the beginning of say 20th century. Now, but this primitive tool is still getting used. For why? For what reason? Because high speed steel, though not comparable with respect to compared to carbides or ceramic in respect of say hardness or wear resistance or chemical stability, but they have got certain unique properties such as the transverse rupture strength, which is very important property for cutting tool, transverse rupture strength, then the fracture toughness, it is easy to form, that is formability, then grindability and low cost. Because of these unique properties of high speed steel, these are still used in industry along with other modern cutting tools, but not everywhere. These are used for some cutting tools which have got very difficult geometry or configuration like drills, milling cutters, hobs, gear shaping cutters, form tools, taps and dies and so on. Now, let us come to drill. This is a high speed steel drill. Okay. Now, this is the axial view of the high speed steel drill. These are the this is the one main cutting edge and this is another main cutting edge, and the speed varies along the cutting edge. what is done along the cutting edge, some grooves are cut. Here you see the grooves are cut on the main cutting edge. These grooves can be cut along the rake surface in this diagram, along the rake surface or along the flank surface, both are possible. Now, one thing you see that this chip breaker and these two chip breakers should be offset, because the material will not be removed by this cutting edge here, that will be removed by this portion. So, the grooves cut on the cutting edges should be offset, so that the entire material gets removed, and this is the chip breaking in high speed steel drills, either cut on the rake surface or on the flank surface. Now, these are little complicated. Now, this can be simplified by another two designs, these two. What is this? In this case here you say this is round, very easy to manufacture, this is done by milling cutter. Instead of cutting as a round, so simple, you make a ridge here, a ridge like this. What is the function of this ridge here? When the chip will be formed by this cutting edge, this ridge will force the chip to curl tighter, more close curling. As a result, the disposal of the chip will be easy, that will not jam into the space, or it will not damage the internal drilled surface. So, this basically does not break the chip, but this will force the chip to curl closely, and the chip will come out more easily without any disturbance and obstruction. This is further simplified by the earlier. Normally, this is sharp like this. By removing this portion by milling, the one heel is created here. So, this will force the chip to curl closely, and that will make the chip disposal and collection convenient. Now, this is applied to milling cutter, end milling cutter, slab milling cutter, and also in case of say broaching cutters. Now, here you see the milling cutter here, and this is a helical milling cutter. These are the cutting edges, the flutes are the cutting edges. On the flutes, the grooves are cut, small grooves are cut. Actually, what happens? In milling, suppose this is a milling cutter, cutting tooth, and this is the workpiece. So, this will move in this direction, rotate in this direction. So, this chip will be formed. What is the shape of the chip? This is just like a comma, and with this is the width, this is the width, and this is the thickness. But in milling process, the chip is automatically, it is inherently broken into pieces. So, as such there is no problem, but the problem arises when the width of the job or width of the cutter is very large. Then this width, the chip becomes short in length, but becomes very wide like this. So, removal of this kind of chips again makes a problem, disposal, collection of such kind of chip become problem. So, this needs to be broken laterally like this. Now, here you see that the grooves are cut, this is the chip breaking grooves are cut, and but offset this distance and this distance you see. So, this will be in a the grooves will not be cut in the same distance from each of this will be offset, so that the material will be removed throughout the work surface. And these chip breakers, this kind of chip breakers or the grooves can be cut in say nowadays this kind of helical or solid helical or straight fluted slab milling cutters are made of say carbide also. In case of carbide, this can be grooved by special grinding or slight additional grinding. In broaching also this can be done. Now, let us discuss about something dynamic chip breakers. What is dynamic chip breaker? This is very interesting. This is one, the dynamic turning. There is a process called dynamic turning. It is a special technique really. What is a special technique? When this, suppose this is the cutting tool, is a turning, simple straight turning process, and the chip, this is the feed direction and this is the cutting direction. Now, this is the cutting velocity and this is the feed direction. So, chip will flow straight and this is a steady cutting condition. The contact between the chip and the rake surface will remain constant. That means, this is the rake surface and the chip flows and this is the contact area. This contact area is bulk contact or solid contact. As a result, the cutting fluid that you apply will not enter into this region, the bulk contact. So, this cutting fluid that we are applying is not very effective. It can enter only little extent with this elastic contact, but in the plastic contact region it does not enter. As a result, the cutting fluid that we apply is not very effective. Now, in this process, in the dynamic process, the cutting tool is oscillated or vibrated in the direction of feed in this direction, all right, with a small magnitude and medium frequency along with the continuous feed in this direction. So, this feed and this oscillating feed will continuously continue. What are the effects? The purpose of such dynamic machining is a multifold. One, because of this oscillation, this cutting tool will oscillate, this contact will break and join, break and join. So, the cutting fluid will be pulled inside this contact length. So, this effective this cutting fluid will more effectively, that means cooling and lubrication will be more effective. As a result, the force will come down, the tool life will improve, wear will come down and so on. Beside that, because of this oscillatory motion of the cutting tool additional, the feed mark that is produced on the job due to turning, that will be removed. So, this surface will be very smooth because of removal of this crease by this oscillatory motion of the cutting tool. But what about chip breaking here? Here you see that this cutting tool, if you take a section along the orthogonal plane, this is a chip flowing. So, this is oscillating. So, this is the path. The previous path was like this, it was oscillating, and now it is going to cut in this direction, not a straight path, because it is oscillating. Now, these two waves, the wave already cut and the groove going to be cut, these two waves may be aligned or may be offset by 90 degree or any degree. Now, if it is offset by that one, you see this chip come out in the form of beads and the neck is very weak. If there is slightest obstruction from this side, then this will break into pieces, just like small beads, it will come out. So, this kind of dynamic turning will not only help improving the surface finish and make the cutting fluid action more effective, but also enable chip breaking automatically. Now, this is another kind of dynamic machining called dynamic facing. Say this is an example. Here is a layer of material is going to be removed by the facing operation. The tool is moving in this direction, there is a cross feed, job is rotating as usual and the material is going to be removed and the chip is coming out continuously. If the chip comes out continuously, there will be continuous contact and there will be no effective cutting fluid action and surface will be also rough. Now, if the cutting tool is given an additional vibration in this direction, the direction of feed, then the surface will be smooth, the cutting fluid will be more effective in cooling and lubrication, and at the same time the chip will take this particular shape and that will break into pieces. Only thing is that this frequency and amplitude of this one has to be carefully chosen in with respect to the feed or cutting velocity, then only chip breaking will be more effectively obtained. Now, what are the overall effects of chip breaking? Let us summarize. Now, there are two types of effects, favorable effect and unfavorable effects. What are the favorable effects? Safety of the operators. As you said, if it is not broken into pieces, if it is allowed to move very fast as a sword, hot sword, as I told you as an analogy, then it will be very dangerous to the operator. And I remember while doing PhD, my PhD in my earlier days, one of my colleagues, he was conducting one experiment on machinability of ductile material, say steel, at high speed. Chip was coming out. So, for research purpose, he used say flat type, negative break flat type cutting tool without any chip breaker, and the cutting speed was increased. The chip was coming out very fast, and it was creating problems. So, he tried to catch hold of this chip and break it or hold it or pull it, but it was so sharp, high speed and hot that even when he caught it by a very solid and strong leather gloves, he had deep cut beyond the glove, which also got cut, and we found profuse bleeding which happened. It can go to that extent. So, this chip need to be broken at immediately after coming from the cutting zone. So, safety of the operators, that is achieved by chip breaking, that is the most important favorable effect. Convenience of collection and disposal of chips. Yes, the chip will be automatically broken and fall into the container or the screw conveyor, and that can be easily disposed of. If it is allowed to come out continuously and tangle throughout the workshop, then it will create problem. Protection of the finished surface, that if the chips are broken, they will not strike on the finished surface nor on the tool. So, both the tool and the finished surface will be protected. More effective cutting fluid action. Now, as I told you that because of this pushing the chip upward by the heel, the contact length between the chip and the tool decreases, and through the small contact length the cutting fluid comes closer to the cutting edge or the chip tool interface, and then the cooling and lubricating effect becomes more effective. As you see that this is the cutting tool and the chip tends to flow like this. Now, if you have an obstruction, the chip will flow like this. So, there will be more space. If it goes like this chip, then there is a bulk contact, but if the chip goes like this, you get small contact and the cutting fluid will come into this region and be more effective. So, more effective cutting fluid action, that is lubrication, cooling and so on. As a result, the tool life will be higher, the cutting power consumption will reduced, all etc. But what are the unfavorable effects? Since the chip is growing and breaking, coming out and breaking, so there will be fluctuation in the cutting force. As a result, some vibration will take place, chance of vibration and the consequences like damage of the tool, fatigue failure of the tool, or say damage of the machine tool, and all these problems may creep in. More heat and stress concentration due to shorter chip tool contact. Yes, again I tell you that if the chip is obstructed by a heel, then this contact length will be very small because of this obstruction. Otherwise, it could go like this and contact length would have been wider. If it is wider, then the stress, the force will be distributed over wider range. But if this heel is applied, obstruction for chip breaking, then the contact length will reduce. So, the heat and stress will be confined in a small region near the cutting tip, and there will be lot of stress concentration and heat concentration. As a result, there will be chance of breakage or chipping or plastic deformation. Hence, it is said for more heat and stress concentration due to shorter chip tool contact length. That is why this sharp corner should be provided negative band and then rounding to provide the mechanical strength as well as heat dissipation. This is needed. Now, come to some exercises. After learning the entire lesson, you will be able to solve the problems, and I have given few lessons. Question number 1, what factors are considered while designing the rake surface or the cutting edge of carbide turning inserts? Now, what are these? That will be answered later on. Next question, in which direction is the cutting tool vibrated and why in dynamic turning? Is it in the axial direction or cross feed or in the tangential direction? That has to be answered. Why are the step type indicated chip breakers made angular? You see, the step type chips are angular, radius, parallel. Why sometimes it is made angular? What is the advantage of making angular? When is forced chip breaking necessary and why? This is explained number of times, so answer will be very easy. Now, the answer of question number 1, factors considered during design of the inbuilt chip breaker along with the chip breaking. Along with chip breaking, what other factors? Enhance thermal and mechanical strength of the at the sharp edge, reduction of the cutting forces, by more effective cutting fluid action, which will also help in reducing the wear. Now, answer to the question number 2, tool is vibrated in feed direction only in case of dynamic turning. If it is vibrated in transverse direction, then the surface will be rough. If it is vibrated in tangential direction, then the effect will be less, the chip breaking effect, and it is more difficult to provide. The answer to third question, the chip breakers are made angular to shift the chips either away from the operator or away from the job according to the necessity. And finally, the forced chip breaking is necessary when continuous chips form and come out very hot, sharp and at high speed, that is very dangerous. Under the condition work material is soft and ductile, flat rake surface with a positive or favorable rake angle. For why it is given forced chip break is necessary? Safety and convenience of the operator, easy collection and disposal of chips. Thank you. So, this is the end of